Hello and welcome to the Topography and Contouring Lab Makeup video. So this will be broken up into two separate videos. In the first video, I'm going to go over the lecture slides, just the background information you need to complete the exercises. In the second video, I will actually walk through the exercises to make sure that everyone has the same understanding of the assignment and can maybe see some common places that people miss out on some of the exercises. I highly encourage you after this video to go ahead and give the exercises an attempt on your own before watching the walkthrough video. It will greatly improve your understanding of it and help you out on the homework assignment that is due for this lab. So, topography refers to the surface elevation of the land. Their topographic maps are detailed maps that show the surface features of the land. They show the shape and form of the landscape and allow you to see some of the geological processes that develop landscapes and landforms. So they help your geologic understanding on how a surface feature might have been formed, especially large-scale features that you might not be able to see just from an individual perspective standing in the area. Topographic maps use contour lines at set elevations to visualize the relief or the elevation of the landscape. It is, in effect, a two-dimensional representation of a three-dimensional landscape. On these topographic maps, you can see locations of features such as rivers, roads, buildings, hills, etc. And they're constructed qualitatively at various scales using tactics such as land surveying, remote sensing from satellites or aerial vehicles, using geostatistics, and even trigonometry can be involved in developing topographic maps. I know many of you might have seen topographic maps before, but this will also be a good experience to build the background of those of you who are unexperienced with them or haven't even seen them before. So on the right here, of course, is an example of a topographic map, and you can see it might look like a mess at first if you've never seen one before, but that's okay. We'll get through this all together. So you can see here marks, I believe, a road. All the different areas of the map are labeled, and you can even see features such as a lake, and basically you can tease out all these different surface features of the landscape by looking at one of these topographic maps. So as an example here, over the next couple of slides we'll be looking at Mount St. Helens. On the right here is a digital elevation model, which using either satellites or planes or helicopters equipped with the right technology, we can actually develop a three-dimensional render of a landscape. So that's just a 3D image right there, developed by a computer. On the left is the same image, but overlain with a topographic map of the area. So these contour lines that make up a topographic map refer to a specific elevation. So the contour lines change with elevation. Going from one line to another means you're either going up or down in elevation, whereas the contour shapes reflect the landscape or landform you're looking at. So looking at this topographic map here of Mount St. Helens, you can see that all of these are concentric lines. They don't, it might be hard to see, but they don't cross or really touch each other. They're very close in many areas, but effectively, if you had a large enough map, they wouldn't touch at all. As you see in the middle here, where it's flat lying or more gently sloped, these topographic contours are more spread out because that same change in elevation between the lines is spread out over a larger distance. Along the edges of the horseshoe shape that make up the mountain, you can see that the contours are much closer together, which shows that it's a much steeper surface. Jumping back a slide here, you can see that represented in these three-dimensional representations of Mount St. Helens. You can clearly see it on the right, but with that overlain surface, that 3D model overlain with the topographic map, you can really see what I'm talking about here. So each contour represents a specific elevation. So where these contours are closer together, you have that steeper surface, the horseshoe of the mountain. Whereas where the contours are more spread out, you have a more gently sloped or even flat lying area. Showing this again, because it's a two-dimensional representation of a 3D surface, you might run into something like this, where you see several concentric rings of contour lines that represent a set of peaks. It's important to label these contour lines, though, because with poor or improper labeling, you wouldn't be able to look at those top rings and say whether it's going up or down. Because several concentric rings on a topographic map could represent a peak or a hill coming out of the ground, or it could even represent a basin or a depression in the ground. It just depends on if that surface is increasing in elevation or decreasing in elevation, which is why that labeling is so important. So there are several rules for making a topographic map. These are in the lab manual on page 55, but just to walk through them here, I have them all listed here. So first, the contour lines themselves never touch. Um, on some maps, if the scale is a little tight, it might look like they are, but on a large enough map, you won't ever see the elevation lines, these contours, actually touch. For similar reasons, you will also never see them cross. If they are touching or crossing, what that would mean is that one specific point from a top-down view of the land is at two different elevations, which really doesn't make sense. They also never dead end. So imagine a three-dimensional surface jutting out of the ground. You wouldn't have a spot where it suddenly just stops being 300 feet. There's always going to be some point of it that's at a certain elevation. If it's on a scale where you can actually represent it on a topographic map. So really, what it comes down to is when we're constructing topographic maps or drawing with contours, they just don't dead end in the middle of your working area. So you can have concentric rings like we see here, where the contour line eventually comes back around to where it started. Or more commonly, most of them will end up running off of your work surface. Eventually, on a large enough map, they would turn around and eventually make a loop, but on most scales, there are at least some contour lines that will run off the edge of the page. So contour lines also never separate. If a contour line would separate, that typically means there's an elevation you're not paying attention to. So in a functional topographic map, you never really see that. So that's something to keep in mind as we construct these. Also important, these topographic contours will V upstream. So if you look at this image on the right, you see the stream coming down from north to south, effectively, from top to bottom here. So a stream bed is cut into the land surface. That's why the water goes in that direction and is pooled in here and can flow along this consistent area in a stream, is because it's cut into the surface. So that's why they V upstream. Basically, if you look at the cursor where it's at right now, that's on the one side of the stream. As you move towards the stream, you cut across that contour line, and even again, representing you're jumping down in elevation, which makes sense because this is going into the stream bed. So as you go down into a depression, you're getting to a lower elevation and therefore a lower contour line. So if I go straight to the right, you see me go from the 400 down to the 380 contour, which makes sense, which means that the stream bed going from here to here is about a 20-foot drop. Pretty steep, but it happens. So contour lines that are closer together are steeper. Basically, the difference between two contour lines will always be consistent on a map. Um, some combination maps have marked out areas where there are different, but basically for one consistent surface of a map, that interval between two lines is always going to be the same. So if you see on this image, you have a 300 bold line marked and a 400 bold line marked with several lines in between. So basically, there's 5 jumps here. So you go from 300 to 320 to 340 to 360 to 380 to 400. So this is a 20-foot contour interval. So what that means is that there's 20 feet in elevation difference in between each of these lines. So just as a broad example, at this bold line, you're at 300 feet elevation. These are typically in reference to above sea level. So this is 300 feet above sea level, and then this line represents 400 feet above sea level. There's several intermediate lines in between to represent more clarity on the map. Also, and I cannot stress this enough, it is extremely important to label your contour lines. It is very easy, especially in more complex areas of a contour map that you're making, to get lost on what line you're actually working on. So if you start on one side of the page and you're drawing, let's say, a 400-foot contour interval, and when you end on the right side of the page, or the other side of the page, you're drawing it as if it's a 500-foot contour interval, then that doesn't make sense, and you're going to need to redo that. And that's really easy to mess up if you're not labeling your contours. So for these exercises, I highly recommend you label them as you go, but it is required for these contouring assignments that you do label your contour lines. What elevation are they representing? Once again, all these rules are in your lab manual on page 55, so it's there for your reference as you work through the assignments. Last thing we'll go through are topographic profiles. So a topographic map represents the landscape in a top-down view, so a bird's eye view. A topographic profile represents it from a horizontal view, so looking at it from the side. How we do that is you take a topographic map or some other map with some sort of contour, and you draw a profile line across it. So here we have A to A prime. At the bottom here, we have a profile set to the same length as that line we just drew. And I'll go through this more in the walkthrough video, but basically everywhere one of these topographic contours crosses this profile line, you can mark on that scaled line below. So here, for instance, on the very edge is about 1,100 feet. So somewhere in there is 1,100 foot contour, and you just carry that straight down and mark the point at 1,100 feet. And then when you go up, every time one of these contours crosses, you can make that note and put it at that same distance along the profile. So let's say we're so far in on that profile line, you go so far in on this profile and mark that elevation. And you can do that along the entire length of the line so you can get a clear view of what this would look like from the side. Geologists often use these topographic profiles to help generate cross sections so we can understand deeper surface elevation features. So you might see a excuse me. You might see a geologic map that has these separated at certain different geologic units shown at the surface that truncate at certain points along a profile, and then you can put that on this profile, and then based off of field measurements can draw which way those layers are dipping in the surface, or if they're flat lying, you can see that sort of thing. So it's very handy as a geologist to be able to make a topographic profile based off of a map. So that's the intro video here. Once again, I recommend that you work through the exercises on your own first using pencil so that you can erase if need be. Keep all these rules in mind on page 55 in your manual as you work through these two assignments or these two lab exercises on the following couple of pages. And then once you've gone through those, or if you hit a wall, go ahead and look at the walkthrough video and we can go through that exercise together. If you have any further questions, feel free to send me an email or stop during my office hours, which are Monday from 3 to 4 p.m. If that doesn't work for you, you can always email me and we can work out another time throughout the week to meet. Best of luck.